Hello, my name is Zhong. I'm from Huawei Cloud. The topic of my presentation today is a cloud-native memory-optimized database engine, HiEngine. I will introduce this paper from the following aspects. Memory-centric computing has become the research focus in academic and industry. A new persistent memory filled the gap between DRAM and NVM, such as Intel Optimum memory. Memory-centric database becomes the hot interest, such as NAMDB, HydroDB, and FARM. Customers who migrate applications to the cloud need cloud-native in-memory or LTP solutions. Existing cloud database systems are mostly disk-resident databases that follow a storage-centric design, such as Aurora, PoloDB, GhostDB for MySQL. They have following features: block-based I/O, page-oriented layout, and a buffer pool. Especially, they have a buffer pool that in-memory database do not, which directly affects how to architecture the engine and exploit hardware performance for in-memory databases in the cloud platform. However, most of in-memory databases are designed based on on-premise solutions and do not directly work in the cloud. Although, for disaggregated in-memory databases such as NAMDB can provide cloud-native feature, they behave expensive access latency across the network. As for modern cloud infrastructure, PM, persistent memory presents both opportunities and challenges to the decoupled architecture. We can equip persistent memory on computer nodes instead of hiding them behind network I/O, but this goes against the stateless nature of computer nodes. The shared reliable storage service of Huawei Cloud that bridges this gap, it can be built on top of modern SCM using RDMA. It allows in-memory databases to persist locally and remotely within the computer layer without networking round trips. HiEngine also optimizes for ARM-based manifold processes. This paper presents HiEngine, a cloud-native memory-optimized in-memory database engine to solve those challenges. HiEngine introduced persistent states to the computer layer to enable faster persistence and low latency connections. In the computer layer, SRSS leverages persistent memory settings, Intel Optimum memory to store and replicate log in 3 computer nodes. In database structure, HiEngine behaves 3-layer physical and 3-tier logical architecture. The login layer server is co-located with a computer. HiEngine is built around the idea of log is a database, and several key techniques are used. For example, tuple-level memory layouts that use log-free index and MVC systems that achieve durability and faster recovery by using SRSS. HiEngine facilitates data access through rule map that are coded structure in HiEngine to support MVCC, efficient checkpoint, and recovery. From the tuple-level memory layout, some special design to be addressed. Unwording consists of many key fields such as dmin, dmax, next variant, log set, and so on. The leaf node of index is a row ID that consists of the ID and slot ID. The key of secondary index consists of the user-defined key plus current row ID. Currently, HiEngine provides snapshot isolation level. When transaction begins, it is assigned a reader, JSON, and a globally transaction ID, and replace the transaction IDs in dmin and tmax fields with CSN at commit time. Currently, HiEngine provide two kinds of timestamp grant. Vertical clock has 40 microsecond latency, and global clock has 20 microsecond for no atomic clock. Clock is the best choice for timestamp grant, and the performance scalability for in distributed databases according to other innovations. HiEngine organizes data record in the form of logs without the page accept. Partition in direction error maps record ID to record database. PIA has the following benefits. Firstly, update operation of rows will not involve changing the internal structure of index. Secondly, the key of the secondary index consists of user-defined key and another key. Thirdly, checkpointing becomes lightweight as one only needs to persist the PI instead of real data. Lastly, recovery only rebuilds the PI instead of in tuple words. SISS provides an open-only abstraction and a segment structure with payload. HiEngine uses distributed logging on the computer side. Transactions become committed so as the log records are persisted to the computer side persistent memory. The log is batched and flushed to the storage layer synchronously. To accelerate recovery, HiEngine runs checkpoint in background. Checkpoint becomes very lightweight and only needs to persist the PIA. Recovery consists of the load phase and the replay phase. The recovery is finished once the PIA are set up. Later accesses will bring data directly from main memory demand via. We also design a parallel recovery. HiEngine will fix the offset in PIA or synchronously when finish the log compaction. In HiEngine, the modification of index tree will not be persisted immediately. Index tree's checkpoint is similar with log structure merge tree. Unfortunately, read amplification exists. HiEngine proposes two deployment modes. This paper focuses on the vertical integration. So HiEngine coexists with the existing DB engine in DB from a circle. User only needs to declare engine type in create table statements. The queries will then be routed to the corresponding storage engine. In memory databases, the high performance of transaction engines is severely underperformed when the native circle engine is involved, which is related to the efficiency of interpreted execute and networking latency. So HiEngine implements the code generation and provides code generation cache. We compare HiEngine with three other industrial strings systems by using Sysbench and standard TPCC benchmarks. All evaluations are conducted two kinds of environments, single server and cloud SISS with persistent memory. HiEngine significantly outperforms DBMS.m on both platforms. Single server performance of HiEngine reaches up to 35 million TPMC. The end-to-end performance is greater than 50% under compiled execution. We evaluate the ARM-oriented optimization by setting memory allocation policy and workload partition. HiEngine storage engine outperforms DBMS.m by 60% in all cases. According to the analysis for TPCC model on ARM platform, the performance decreases by 5% for every 10% increase in closed-circuit remote accesses. The optimized ITO performance was improved by 10 times. So, in summary, this paper presents HiEngine, a cloud-native memory optimized in-memory database engine that endorses hierarchical database architecture. It leverages the modern cloud infrastructure with computer-side faster persistent memory and brings the benefits of in-memory database engines to the cloud. Another coexists with disk-based engines. Besides, it provides comparable performance to on-premise in-memory database engines. Thank you. Thank you very much.